So we have quite some time. So as we move into the discussion, perhaps Miriam, I would like to start off by bringing a question back to you. I'm aware that you've worked in some very interesting field settings that have even more elements of complexity than which you presented in this talk. I was just wondering if you have any perhaps interesting stories that you could tell to sort of elucidate some of the points you made in your talk.
Sure, yeah. Maybe I could share a bit of my experience working in Nigeria and responding to outbreaks like cholera and measles. And it's in a context where there's conflict in northern Nigeria, and because children are not able to keep up with immunization, and there's a lot of displacement. So when you get children mixing in an environment where some are vaccinated, some are not, it's really a good ground for an outbreak to occur. And sometimes in remote settings, it's very difficult to collect that kind of data. And sometimes we have to do it remotely because you cannot be on site. And it takes a lot of coordination, the logistics, including experts who are on the ground and those who are supporting remotely. Data sometimes was a difficult, it was a challenge to get data. And with cholera, we needed to get data on the go, real-time data, to be able to know, to add some special element into it, to be able to know which are the next targets, which are the next districts that we need to be concerned about. So yeah, mainly from outbreak response, but also measles is a similar situation in such context. And data is really crucial in terms of how the outbreak goes and being able to plan timely responses.
I mean, it's absolutely fascinating that when we think of the complexity of going into a conflict zone where there's quite a deadly outbreak and all of the political and social factors that are involved. And as you've listened to the previous talks this morning, is there anything that really jumps out that, oh, maybe if I was to collaborate more with that person or draw from that particular discipline, it might really help?
I think climate has a lot to do with how disease evolve. And as we are talking about climate change at this point, we have issues of drought, we have issues of a lack of food security is an issue. So climate certainly is one area that could collaborate closely with epidemiological modeling, yeah.
Thank you. And do any of our panelists wish to come back on that or ask one of each other a question, or shall I move to some of the questions from the chat? Okay, we'll keep the questions coming, and do just raise your hand. I have a question for Georg. As a pharmacokinetic modeler, one thing we love to do is, as many of the approaches, we try to do the trials that we can't actually do through simulation. So we simulate various what-if scenarios, and then we produce our sort of confidence intervals to sort of see how accurate by simulating, say, 1,000 virtual individuals. Is that something that you do? Can you like simulate 1,000 Earths and different things that happen to them?
That depends a bit on the model you're using, because as usual, it's always a compromise, right, between what you want to do and what your computer can actually do, right? So,
sure.
Yeah, because of that ever-increasing complexity and spatial resolution of the most comprehensive models, they really have difficulties running 1,000 simulations, right? You cannot do that, but there are classes of models, you know, which take some compromises in, for example, the spatial resolution, run it at a coarser spatial resolution to get things faster, and then you can do these ensemble experiments, testing various what-if scenarios. And this is actually something we routinely do, right? So, but even, you know, with the comprehensive models, even those future projections, right, under different assumptions about our socioeconomic future, are what-if scenarios in a sense, right? So what if we behaved in a certain way? What emissions can we expect, and to what, you know, climatic outcome this leads? But we also do it to test for uncertainties, or, you know, since, you know, climate is average weather, and weather has this stochastic chaotic element to it. We also do like ensemble simulations, but just slightly perturbing initial conditions in our models to see how this affect the end state. So indeed, we do that. And there is even, climate science is very strong in model intercomparison projects. So comparing different models forced with similar or the same boundary conditions. And there is even a model intercomparison project called the What If map, right? Exploring, potentially disastrous future outcomes if, some of the feedbacks would all go in the same direction, for example. So yes, this is something we routinely do.
Miriam.
Yeah, so you said maybe if you could ask a question to the other panelists. I often get asked when I speak to people, when I interact with people, especially people who are finishing their masters and their PhDs. The question is always, is there a clear career pathway into what you're doing, or did it happen by chance? And just wanted to hear from the other panelists whether there's a clear pathway into modeling in your particular discipline, or whether it's one of those that you happen by chance, or because you have a mentor who somehow pushes you into that direction?
That's a brilliant question, and it does actually reflect some of the questions we haven't answered in the chat. I'm going to go in the order of the people that are laughing most. I'm going to start with Georg, then go to Johanna, then Steve, then Patrick.
That's an interesting way of getting attention, or getting first in the line by laughing the most. Yeah, I mean, that's an excellent question, Miriam. And I think speaking as a climate scientist, more from the physical climate science, I guess, no, there isn't a clear pathway. And it's reflected in the background of the people working with me, for example. So we have physicists, of course, some have a meteorology background, but not many, right? But we also have mathematicians, people from various, physical science disciplines. And we are not trained per se as Earth system modelers or even as modelers or software developers, right? This is usually something people pick up on the side because they're interested in it and learn by doing, right? Which is also not ideal, right? And poses some challenges. But, a clear pathway, I would say no. Which is partly due to the interdisciplinarity of the whole endeavor, right? If you want to model the coupled Earth system, it is interdisciplinary by definition in a way, right? And also that modeling and simulation is sort of still a bit of the newcomer, in how science is done. And there is, universities are beginning to pick that up and do more formal training in coding and programming, and so on. But it's still, there's no clear official pathway how to become an Earth system modeler, for example, right? So it's something which usually happens to people somehow.
So was there for you like a particular turning point that you thought, this is the way that I can use the skills I have to make a better world?
For me personally?
Yeah.
Well, I've sort of had a not really linear career path, in the sense that I started out as an observational astrophysicist before I moved into climate science. So this is maybe a good illustration of what happens. And as an observer dealing with cloudy nights and broken instruments and all sort of technical problems, I always envied the modelers in astrophysics, because I thought they just press the button and then publish 3 papers in a row. Now that I'm a modeler and know all the difficulties of model development, of course, I have a slightly different view of the challenges of modeling. But the turning point was essentially that for me, I think astrophysics is incredibly important culturally, but I wanted to do something which is more relevant for the future of our society. And then I moved into that and moved into modeling at the same time, right? And I don't regret it by all means, right? But it's not something which was sort of planned from the beginning, right? It just happened.
Thank you. And Johanna, did you always see yourself as becoming a health economic modeler?
No, not at all. I think my answer in general for this field is very similar to yours, Georg. I think most people don't start as thinking they will become health economists. There's two general pathways for people. So there's people who study medicine or medical related fields, or people who study mathematics. And at the end, you sort of need to combine both. So I started more from the medical side, but later on trained in mathematics as well. And I think for me, the turning point personally was that I realized I'm not as practical person as I thought I will be. So I'm more interested in the theoretical aspect of things. And also it's interesting for me how data can be used in decision making. So that was, yeah, there are these days some university programs that train health economists specifically, but I think most people who work in health economists still did not go through these programs. So you can go either way. But yes, the main thing is interest in mathematics and how you can use data to inform decision making.
Thank you. I can't quite remember if it was Patrick or Steve next, but I'll pick on Patrick.
Yeah, thank you. That's actually a brilliant question. I'm actually heading a study course which is called agricultural technology, which is a very wide field. So people start working with geographic information systems. Others are more interested in mechanical engineering. Others are more interested in plant production. And what my experience is that I've seen a couple of times that students saw a certain topic or saw a certain theme and they were suddenly enthusiastic about it. And I think enthusiasm is the basis for doing something really good. And I think this includes modeling. What I find difficult about modeling is modeling by itself does not help, right? So you need to be good at physics and mathematics, and at the same time, you must have a certain domain where you're working in. And so for the last 20 years, one of my main jobs was basically to bring software developers and agricultural scientists on one table, and then to translate between the two of them. It's not because one was speaking English and the other one was speaking German. They were both speaking German, but they were both living in totally different worlds. And I think this is a big, at least in agricultural sciences, a big issue in modeling. And yeah, I also feel very much with Georg. Instruments can break, but at some point you can find out that models can break as well. So everything is breakable in this world. And well, to summarize that, I think you need a lot of enthusiasm, a lot of interest and passion for it. And then I think almost anybody can become a good modeler.
Thank you, Patrick. It's almost like that Japanese concept, isn't it, of ikigai, you know, the thing that you're good at, but the world needs, and you've got that sort of extra kind of passion that means you don't give up. And it's interesting as we move to Steve that I'm seeing some comments in the chat, somebody who has actually been doing like some sort of voice analysis and looking at sort of disease patterns through the way the voice changes, and that also requires different inputs of data that could something that perhaps we hadn't thought of. But Steve, did you always see yourself doing what you're doing now, and how did you get into it? Is there a career path?
Well, there's definitely a career path in the clinical pharmacology quantitative modeling side of things, and it's actually interestingly had a long history. I actually approached it from engineering, right? Was a mechanical engineer by training, working on control systems, who then started to make delivery systems for medications and thought, I probably ought to understand something about the dynamics of those medications if I'm going to develop the right delivery system. So that was the catalyst for me, but subsequently found that, you know, going back to the 1970s, people were doing a lot of strong calculations for improving clinical outcomes with medicines. And then actually, you know, even further, if you go back, there's a long history of using quantitative analysis in pharmacy. You could also say that Paracelsus started it in the 16th century with his famous quote of "dose makes the poison," and really figuring out how do you optimize dose for an individual. It even goes back actually to the Merton calculators in the 1300s. It's an early 14th century group at Merton College in Oxford, one of whom actually left at that time and ended up in Padua, and was the first recorded effort of people using quantitative analysis to estimate dose. So it's got a long, long history in pharmacy, but interestingly now it's actually, I think, undertaught in pharmacy schools and actually being populated heavily in the field of what's called pharmacometrics by people coming out of engineering and more mathematical inclined backgrounds and trainings. So still a lot of opportunity there because all of drug development relies on this kind of modeling to come up with optimal dosage, to estimate the right dose to administer to a patient. And I think as we've started to understand the opportunity for characterizing individuality, particularly with the genomic revolution that's going on, it starts to then add a huge amount of dimensionality into this field that will only be solved by better models and stronger computational power.
Thank you, Steve. I've been told my sound is breaking a little, so if it does, wave your arms or something so I can tell. I do think this diversity of our backgrounds is actually really important, and in pharmacokinetics, it's really interesting when you work with a basic mathematician who is learning biology with people that have come from a more biological background who are learning the mathematics, because we sort of approach the same problem from the other side. And I find that that often helps us find solutions we wouldn't have found on our own. Miriam, you're not quite off the hook because you were the one that posed the question. So I think you need to answer it for yourself too.
Sure. I think especially in low and middle income countries, sometimes a pathway, a clear pathway into clinical research is not always so apparent. And sometimes we happen into it because you probably have a mentor you have worked closely with, you have some interest in that area. For example, if I look at maybe clinicians working in low and middle income countries who have an interest in getting into research, when you look at the patient-doctor ratio that is existing within Africa, it's almost impossible to do the patient work and also do research. And also the reward system, I think within low and middle income countries sometimes can be, you're probably rewarded more for the number of patients that you see and not for the publications or research outputs. So for me, I think it was a combination of interest in terms in the health sector, but also understanding what diagnosis and means for a patient journey. Once you get a diagnosis, what does that mean for your ability to work? What does that mean for your ability to still have normal family life? So wanting to understand those social determinants of health somehow led me onto a path of epidemiology. And I wonder whether there's a place for having, when I look at the UK, maybe sometimes people who are clinicians, they somehow have a clear pathway how to progress. But in low and middle income countries, I think that is less and less defined.
Thank you. Now, I think we can all, I'm seeing a lot of nods and a few comments in the chat that these answers are really quite helpful, because many of those who have joined the webinar, I know, are people who are interested in perhaps going into this as a career option, or maybe they're already doing that. And one of the questions that has just popped up, maybe any of you could answer, is that are there certain skills that are really sought after in mathematical modeling if you want to advance in this field? You know, are there any things that you would look for? You know, if somebody is asking themselves the question, could I do this? And you were their mentor, what kind of skills and background and things would you want them to have?
I think one thing that we are often quite short of is people who can do the quantitative part, but also be able to talk about it. So sometimes you get one, but not the other. So I think the communication skills that cannot be underestimated. So it is really good if you have that mind for mathematical modeling, interest in learning that, but also at the same time, interest in working on communication skills and how you can talk to other people about it.
Yeah, so being able to talk to other people about it, I think, is also something quite key. And I think that's something that we're actually doing even right now. But how, as we get more and more technical, do we find ways to make that accessible to the people that are going to be making decisions based on our models and our findings? And I know that's something that we often end up coming back to in the pharmacometrics community. But Georg, I see your hand is raised.
Yeah, just a few comments. I mean, you need some analytical skills and some love for playing around with numerical models and some enthusiasm, as Patrick has correctly said. And also, I fully agree with Joanna. You know, trying to having communication skills is important, and this has two directions. Catriona, you said communicating that to stakeholders, decision makers, right? That's obviously an important dimension, but also since at least in climate science, system science, it's inherently interdisciplinary, right? So we have experts, disciplinary experts from different disciplines working with each other on these models. So you also have to be able to communicate within the group, right? And also to communicate with computer science experts, right? And Patrick, you said that, pointed this out. I also have. I'm really lucky to have someone with a computer science background on my model development team, in addition to all the, physicists, biologists, whatever we have there, right? And this is incredibly helpful. And he has, tolerate some of our quirks when we, as scientists, develop models. But also it's incredibly helpful for us to learn from him, how proper model development should actually be done, right? So this is also part of the communication aspect. So it's really, my advice would be, try to get some experience with modeling, coding, simulation as early on as during your student days at the university, and then try to find a field which interests you, and then go into it with enthusiasm, and try to find a group and a mentor who can help you along with that. That would be my advice, I guess.
Wise advice. I don't know if anybody else would follow up on the same question of what they might be looking to for, or what advice they'd give a young person. But maybe I'll come back to you, Gail.
One other thing I'll quickly
Steve, go
remind.
on.
Yeah, I'll just quickly mention too is to not have so much belief in your models, right? So if you're reporting your models to the fourth decimal point, you're probably missing the point. So I think, to that point of communication, how do you actually get the essence of what the model is telling you? Oftentimes, it's not the numerical answer, it's the trend in which the information is moving, or interrelationship and a dynamic that you actually can expose in the model that otherwise might be difficult to see or comprehend. And so I think that's a key part of the communication in modeling, is not so much on numerical precision as it tells you something about how the system might behave under certain circumstances.
Fantastic, Steve. That's really, really helpful. I think it's realizing the limitations of our models, but still having the confidence in them, but knowing where the limits are. Kanchu, I saw you turned your camera on briefly. Were you wishing to join on this point?
Yes, so I think a really important point is to join multidisciplinary teams at universities who may be working on a singular problem, but the ability to talk to different disciplinary people and communicating with them becomes really important. It's a really important skill to have. Also, when you're in these multidisciplinary teams, you start thinking about the ethics of what you're doing in a very different manner, because everybody comes at it with a different perspective. I think thinking about those kinds of aspects like ethics and, as Joanna said, communications, etc., but in a multidisciplinary team, because I think modeling is a multidisciplinary effort. It's not a single effort. I mean, at least that's the direction I think the world is going. Thank you.
Thank you. And Georg, I see your hand is raised, and with what you're going to say, there's also another question that has come up that I think you are well placed to answer. We've moved from sort of some of the skills, and what's coming through quite strongly is the need to be able to advocate and communicate and inspire confidence. And obviously your work can get quite political, because if you're trying to tell leaders that based on your models, the world is going to be on fire if we do nothing. Have you faced any particular challenges? So I know you have your hand raised already, you might have a second point, but I would love to know about your personal experience of that.
Yeah, first I want to resonate what Kanshu said. That communication is important also, because interdisciplinary teams actually can help, move the field along in different ways. And I wanted to enthusiastically support what Steve said. And in fact, Steve, thanks, because when I spoke earlier, I knew I had forgotten to mention something, and that was exactly the point I wanted to make, right? Don't trust your models, right? Don't treat them as black boxes. And this is sort of the first thing I teach students when they do master's thesis in my group, right? The model tells you something, but then please switch on your physicist's brain and your climate science background and try to understand what's going on inside the model. And that's incredibly important. And there are two great quotes on that. And the first one is, all models are wrong, but some are useful, right? And this is just true, right? We know that our models will never be perfect, right? We can never model, look out of the window, the sheer complexity of the Earth system. We will never be able to emulate that to any, precise degree in a computer, right? It's just sheer impossible. But we can still do useful things with the models. And the second quote, which I also love, is scientific computing is about insights, not numbers, right? And that's also very much true, right? The model tells you some number, but in essence, the model is a tool to understand what's going on in terms of processes, rather than, giving you a precise number. And that actually is a nice bridge to your question, Catriona, in terms of how to communicate that to policymakers, right? And this is a challenge, of course, because there are many things we understand very well in the Earth system, and we understand it well enough to say that any future carbon emissions will lead to additional warming and to bad impacts, right? But we cannot nail that down to a 4-digit number. And so we have these uncertainties, and we somehow have to be transparent about these uncertainties without then saying, we cannot really tell, so don't do nothing yet and wait until we fully understand that, right? So that is a constant challenge. And the other is transparency, because, obviously, there is a lot of resistance against climate mitigation measures all out there, right? From industry, from our habits, and so on. And so what we say and what we project and say about future climate change is obviously something which has implications, right, for societies. And so we have to be transparent also about how we do our modeling. So we were moving open source with our climate models, right? It won't help you much for the complex models because you can't run it on your notebook computer, obviously, right? They require huge machines. But we're moving constantly forward with making our modeling process also more transparent and increasing also the quality in terms of reproducibility of model results and so on. And as I said, climate science has a long tradition in model intercomparison project, right? All these projections I've shown you, for example, in my presentation, they are not based on one model. That would be absurd, right? They are based on 20 to 30 models from different modeling groups around the world. And so you can get a grip of, what the uncertainty is, right? And you'll not be in the situation to trust one single model, which will always have, its deficits. But it is a challenge, of course, right? And sometimes, it gets absurd because people think that because the models are imperfect, we don't know that there is global warming, right? Which is obviously bullshit, to be quite frank, because we see it in the observational data, and greenhouse effect has been known since the 19th century, right? So this is not at all based on models. You can actually show this in lab experiments. But to some degree, we have to rely on these models to see what's going to happen in the future under different assumptions, different what-if scenarios, and for this we need the models, right? And all these deficits are just for us an academic challenge, right? So you say, we don't get the precipitation perfect, so let's work on this. But at the same time, there is this expectation from societies, right? Please tell us how rainfall patterns will look in 2050 in Eastern Africa, right? And if we cannot do this, this is frustrating, and also is a challenge because society somehow expects that from us. And this is something where the societal need and sort of the academic challenge clash in a way, because the timescales, the expectations of the timescales are actually by which we provide answers are obviously different.
No, it's fascinating, and I think we did see this during COVID as well, that as our knowledge and understanding increased, there were some times when then the information being put forward to the public changed, and some members of the public as well took it to mean that the scientists don't know what they're talking about, or even worse, there's almost an accusation that at certain points there had been lies told. And that actually wasn't the case. It was just that we were building up a body of knowledge. And at the time, we were making the best decisions with the limited data and models and things that we had. And as things moved on, things were sort of refined. And I think that question about communication and communicating uncertainty in such a way that you maintain the confidence and credibility that you're trying to inspire. Yeah, Patrick.
Yes, I think confidence is really a very important keyword, because what I see at the moment, or what I experience, is that we've got a lot of diverging movements in society and even in science. And what people are looking for, and especially what politicians are looking for, is simple answers. And they always want to know whether our answers or results are accurate. And as I think all of us agree, every model is not correct, but some are useful. The question is, how accurate do the models need to be? Then you need to start discussing with politicians, what is accuracy, right? What is precision and what is accuracy? So this is difficult enough to explain this to politicians. And I think then we always come to the point where we've been trained as scientists to say, we can never be sure, there will always be errors in our numbers or figures. And if we tell this to a politician, then he says, okay, then we have to wait for another 10 years until you're sure about your results. And then you tell them, we're not going to be sure in 10 years either. And if we can't say that we're accurate or that we're precise, then people are lacking the confidence. So talking about confidence and accuracy or precision is probably something which is very important. And if we talk about statistic significance, we probably have to raise the confidence levels to say, okay, we see a difference between two things. But I think if we want to move forward with the results we have, we need a good solution for explaining that what we say we can never be sure that it's correct.
Thank you. I think some of these quotes, we almost need to produce a set of key quotes from the cross-disciplinary symposium, and that concept of how confident you have to be for it to be useful. I'm seeing a couple more hands coming up. So Miriam and then Georg.
I just wanted to bring an ethical perspective into modeling and just make a comment and say that ethical modeling processes should include transparency and open sharing of data and also codes and methodologies, because that will allow people to scrutinize and some kind of validation from the scientific community, which will go a long way in terms of fostering trust in modeling results.
Thank you. And that is absolutely key importance. Thank you. And Georg.
Yeah, I fully agree with what you just said, Miriam. I wanted to come back to that, what COVID and the discussion of in the public arena actually taught us. And indeed, this is actually I think the main issue is that it's really hard to tell people how the scientific process actually works, right? So it's actually a constant trial and error process in a way, right, with self-correcting on the way. And with the pandemic, of course, we've been been watching that in real time, right? So we got the data in, we didn't know what was going to happen. And so scientists also had to correct their views, as we always have to do, right? This is part of how we work as scientists, right? We do not trust our results. We have to look whether new data match our hypotheses and theories. And for us as scientists, that's completely normal, right? That's the way we operate. But if, the public actually watches this in real time, right? And also, sees that we of course have to adjust, our stance on things given when new data come in and so on. That leads to that perception that we are talking about something, although we are not sure about it, right? Which had to be the case because society required answers in real time during the pandemic, right? And also go back to some of the issues we've been discussing. So I think that also is an educational issue in a way, that maybe not just in the university education, but also the school education level, we have to teach more about how science actually works and how we gain our insights, so that also society is actually better prepared to deal with our findings and deal with that problem of uncertainty, right? Patrick, you also pointed out, right, that we as scientists are, we're used to communicating transparent about uncertainties. But as you said, once we do this as soon as we do this with decision makers, they say, let's just wait, and this is just not what we want to convey. On the other hand, we cannot hide the uncertainties when communicating to the decision makers if the uncertainties are there, right? So that is just very difficult to achieve. But again, I think the fundamental problem is to teach, how relevant are the uncertainties for the decision making problem, right? And how actually does the scientific method work, and how does scientific progress work along the way? And I think there is a lack of understanding both from the stakeholders and the general public, how we actually operate as scientists.
And I think you're bringing in the point there also about perhaps even reaching out into different aspects of society. And I know that I'm a clinical pharmacologist that confuses people at times, because I sort of have one foot in the modeling and I have one foot right out in sort of community public engagement, looking at different words in Ugandan languages that are comprehensible to my team. But actually, we do need to be constantly looking at that sensitization. And I think that's somewhere that also networks come in. And I'm enjoying some of the comments coming through. And Winan Smith is making the point that he's really appreciated the local networks of Pharmacometrics Africa and so forth, where we can actually really discuss these things as specifically applies to our work. Sometimes the way we communicate, Miriam, obviously you'll have seen this many times, but the way we communicate things to people who may have not even had a primary education and who may not have words in their local languages for some of the concepts is really quite different to how we might in perhaps a North European setting, North American setting, where we assume certain basic understanding. And I think this is somewhere where we can learn and grow as a community, but also the need for things within Africa to sort of develop in their own way and think of creative ways. Even this week, we spent several days with a film crew trying to make some modeling for non-modelers type materials, because also the ethics committees, also the regulators, So it's a whole area where I think we can actually learn a lot from each other, and maybe learn from failure too. You know, learn from mistakes, things that we think, oh, if I had my time again and could do that conversation again, maybe I would like to do that better. Steve, Johanna, I don't know if there's anything you would like to bring into this part of the discussion before I start going to some slightly more specific.
I mean, the one thing I was going to just bring up is, and it was interesting because a number of people have brought up the famous attributed George Box quote, right? But he has a couple of other ones, and related to what you just said, Catriona, was this idea that and I think it gets to what Georg was saying of getting his students to really understand how the models work and not view them as black box, right? To find out what happens to a system when you interfere with it, you have to interfere with it, meaning that you've got to perturb your model and really see what happens to it and say, okay, if I perturb it in a way that I expected or didn't expect it, does it still give me the answer that I want? So I think there's some real interesting, realities of how people have used models. And interestingly too, I think if you go back into the late 50s and early 60s, because it was a time when people didn't have as much computational power, they really had to be very careful about how they used quantitative analysis and modeling to be able to draw inference. And I think it did force people to be a little bit more introspective in that regard. I do often wonder, though, because one of the interesting facts about George Box is that he married the daughter of Ronald Fisher, right? So the Fisher exact test. So here you have a man who's known for an extremely precise statistical assessment with small samples, and his son-in-law now is a person who's a Bayesian approximist. And I can just imagine that they had some pretty contentious arguments over the family dinner table at some point in time. So.
Yeah, I guess the only thing I wanted to add was around so developing medicines is so highly regulated business that pharmaceutical companies, they go about and develop phase 1, phase 2, phase 3, and once you get to that stage, you then apply for reimbursement in various places around the globe, and that's a sort of point where you have to make a decision. And I think in the past, if there was uncertainty, sometimes like very high uncertainty, let's say in rare diseases, there was not so much recognition that you can actually continue to collect the data. So you can now, there's more recognition of this, that you can say, we will reimburse the medicine with the information that we have today. However, within this time period, you need to provide additional information. And this could be either from clinical studies, or it could be also real world evidence, which is more how the medicine is working at the population level once it's administered outside the clinical trials. And there could then be a sort of formal review that is done after that period of time. And the other kind of new development is also, or not that new, but fairly recent. So there's early access programs that can be implemented prior to medicine being available. And that allows us to have some data at the time when you want to start the reimbursement at global level. So there's this kind of earlier additional data, as like in addition to the clinical trials, that is coming from the population, as well as the ability to continue to collect that data that will then help us with this continuum of decision making.
Thank you. And as you've put it quite nicely, it's a continuum of decision making. I must say, sometimes that can be a challenge in academia. I don't know so much about how the different members of this panel's work is funded, but often we apply for grants which have, quite a short time frame, relatively, maybe 1 year or 3 years or 5 years. And sometimes there almost isn't time within the time frame of a grant to be able to kind of start to reevaluate and bring in some of that real world data. And I think that is a limitation of how some of our work is already structured. I don't know if anyone has experienced that or has any solutions. Or is my sound breaking? It may be. Is my sound? Is my sound there?
Yes.
We can hear
Yeah,
you.
you're fine. You're fine.
I'm sorry, I'm not sure. I'm not sure if I asked. We've had because of the climate, we're having a very vigorous El Nino, apparently, that is it. And so we're having quite magnificent thunderstorms, which are continuing longer than one might expect, which interferes with the internet. So I'm not sure if that question came up, or maybe it was a rhetorical question about, you know, funding and needing to find mechanisms that support work that has a longer term perspective and kind of completes that feedback loop whereby we can have a hypothesis, do our work, and then go back to our original assumptions and learn and refine. Sometimes I find that difficult within the time frame of a grant. Georg?
Yeah, just maybe commenting on this in a certain direction. I mean, when we are talking about development of complex climate or Earth system models, you know, most funds are actually funding research rather than model development work, right? So this is something we sort of do on the side, right, to achieve a certain scientific goal. But that is not ideal in a way, because if you develop a complex model and you have to do all the quality controls and the validation experiments and, you know, the open source publication and the open data, that actually takes a lot of resources. And if you want to maintain the model and constantly improve it, that's actually not something which is usually paid by the research grants we are applying for. So there is that dilemma actually, not for, you know, smaller models, but for large models. There is really that issue that the funding in terms of research grants is often more short term, and the development of models and maintenance of models should actually be long term. So there is a clash certainly there in my field.
Thank you, Georg. I note that, Patrick, you have to leave the discussion a little early. I don't know if you'd like to make a sort of concluding remark of perhaps something key that you've taken away from today and would like to act on.
Yes, I would definitely find it interesting to work more closely together. I think we already noted that working with modeling and agriculture is complex enough, but it would be interesting to get all the drug aspects as well, and probably try to put together even more data. Because if we dig into the internet and if we look at all the opportunities we have, I think there's quite a lot of data there, which until now only has looked at in silos, in single silos. And what I've learned today is that it would probably be a good opportunity to probably put holes into the silos and make the data flow into two directions. Yeah, and thanks a lot. Thanks a lot for the invitation. Thanks a lot, Kanchu, for making this possible for me to be here. And sorry for some late responses during the correspondence. So I wish everybody a nice weekend and happy Christmas.
You're
Hope to see you
awesome.
soon.
Thank you, you too.
Bye.
Thank you. I will be coming back to that question, by the way. I put him slightly on the spot, but I will be coming back to your sort of take homes and what we do and where we go from here. But meanwhile, Miriam, I have not been ignoring your hand.
No, that's okay. Just a small comment on you talked about funding and sometimes the duration of the funding and however long the project needs to go for. But a different complexity or a different layer to it is also the duration from when the calls go out and to when people need to apply. And now that you're talking about cross-disciplinary collaborations, it means that people have to form partnerships and they have to be equitable partnerships, and those things take time to actually build. They take time to get to understand what different disciplines are working on and the different people are working on. So just wanting to respond to funding, it's not just the aspect of the funding time is short, but it's also the time to form equitable partnerships for cross-disciplinary collaboration.
That's actually really important, Miriam. And I am noticing that some of the funders, for example, the British Academy of Medical Sciences has just put out a call looking at kind of cross-disciplinary work whereby somebody from one discipline can do a secondment in another discipline, really to try and build this. And I think that is something we should be seeing more of in the future, but also agree it takes time. And the equitable, bidirectional, multi-directional partnerships that are actually led from the populations where the diseases in question are prevalent. I think that's really important and something we need to keep in the forefront of our mind as a community. Georg, your hand went up.
Yeah, I just wanted to agree with you, Miriam, that this is another challenge in terms of the funding, that many funding organizations are still, rather disciplinary in their thinking. And once you get interdisciplinary, it gets more difficult. And actually, that's an opportunity for me to answer a question which was further up in the chat directed to me about disciplinary in climate science. And of course, right, we come from our disciplinary background, so we have people working on the hydrology or something very specific from a disciplinary background. But in the end, since everything is connected to everything in the Earth system, we have to really work together. Also, I would like to mention that I'm, as a physical Earth system modeler, I talked about this, very, natural science background for Earth system modeling. But my institute, the Potsdam Institute in itself, is an interdisciplinary institute, right, where we also do modeling of the impacts of climate change on certain sectors, but also do, for example, some economic modeling and modeling of energy sectors, which is then, bridging from the physical side of the Earth system even closer to the decision making, right? So yes, we have our disciplinary backgrounds, but in itself, the institute in itself is very interdisciplinary, and the whole science is interdisciplinary because, to talk to decision makers, it's not just about the physical side of things. It's also about, the economic impacts, of course, and also how, pathways to transform our energy systems, for example, right? And that requires also modeling, but of a different kind than the one I've been talking about. And I just wanted to make this point as well.
No, it's fantastic. A really important point. And I know we haven't exactly answered every single question that's coming through, but I would like to actually reassure audience members that all of your questions are being noted, because this today hasn't been about just those of us on the screen having a nice webinar and saying we've done this, but actually we want to move forward. So what we want is everybody that's participated in any way to be keeping asking those questions. Interestingly, as we were planning the event, there was a lot of email discussion between the different speakers of things that we wanted to get out of this and how we wanted to approach things. And one thing everybody had said, of course, was this very lively discussion, and also that there is no such thing as a stupid question. If you have a question, it is a very real and important question. But my final question is, where do we go from here? So I'll put that to each of the panelists, and I know that Rohan and Kanshu are going to be coming back in, and you can probably then draw that into your conclusions. But Johanna, after today, what might you do differently?
Wow, what a big question. I think it was super interesting to hear the different ways that people are using mathematical modeling. I think some of the details definitely differs between the fields. It would be interesting to dig a little bit deeper in terms of the specifics of the models that we each use in order to better understand whether there may be some techniques that could be borrowed across the fields that maybe hadn't been thought of before. So that is something that sparked my interest.
Thank you. Yes, and I'm aware that we have talked in quite broad strokes today because, as I said, we could talk for 24 hours, I have no doubt. Miriam, what might you do differently?
I guess it would be to keep in mind the cross-disciplinary approach to every research that we are undertaking or every modeling questions, and to see what other data sources that maybe we haven't worked with, what differences those could bring into the models that we build.
Thank you. Steve.
Yeah, I think, I mean, I was reminded of this hearing Francesco mention about the challenge in quantum computing to get the data on the input to be useful, to be able to be used in quantum computing. And I think one of the things that could help in collaboration across all our fields is how do we line up the data from our different models? As an example, I'm pretty confident that the output of my models could be great inputs into Miriam's models and Johanna's models. And it might be that the output of Georg's and Patrick's models are actually inputs into my models, which then pass the baton on to the next, level of models. So I think thinking about how our outputs become others' inputs as a way to start to find those connections may be a nice way to accelerate some collaboration.
Thank you. And Georg, I know you've answered quite a lot of this, but what might you take out of today?
Yeah, I mean, difficult to add something to the excellent things Joanna and Steve just said. I mean, sharing data and thinking about how to share data actually is important. And I agree with Joanna, it would be just interesting to dig deeper into how all of your models are structured, and whether you have encountered problems or different ways of solving problems, which could be applied to my field, for example. And this is actually something which I always thought would be valuable, but it just never seems to be the time to really do that. So today's event certainly served as a reminder to not forget this, because I do think there are these problems where insights, methods from different disciplines actually can help quite a lot, and we shouldn't be stuck in our disciplinary silos. So I guess that would be my takeaway from the meeting today.
Well, thank you very much. And I wish to thank all of our speakers, our panelists, for a very, very enlightening, rich and diverse discussion. I had no doubt it would be so, and I'm really hoping that this is just the start of something even bigger.